Okay, so these are some notes to help you get through the Chapter 6 packet. One of the things that we want to understand is that the total mechanical energy, okay, so you'll see the abbreviation TME, total mechanical energy will be equal to the potential energy plus the kinetic energy. Now, you can take potential energy and as an object falls, convert that into kinetic energy, and vice versa, take kinetic energy as it goes up a hill and turn that into potential energy, but the total should always remain the same. So on page 15 of the packet, which should be, I think, the fourth page that you're looking at, there's a diagram that looks like this. Okay, and then there's several points on it. Up here is point A, down here at the end. It's not labeled, but we're told that the kinetic energy is 40,000 joules, and that the potential energy is 0 joules, which means that at any point in this process, we should have a total of 40,000 joules. So for instance, up here at point A, the kinetic energy is labeled as 0.
Teachers, please excuse the interruption. Seniors, last name Stover through Williams, please come to the...
Sorry, and the potential energy is left blank. Well, we know that there's a total of 40,000 joules of total energy, so the potential energy here must be 40,000 joules. And at any given point along the way, if I can figure out how much potential there is, that'll tell me how much kinetic and vice versa. For instance, right here, we're told at point B that the potential energy was 20,000 joules, meaning that the kinetic energy would also have to be 20,000 joules in order to total up to 40,000. So hopefully that'll help you with that page. The idea is the total is constant. We don't lose or gain any energy. When you go to the next page, page 18 is what we're at. There's a lot of different problems. They all basically deal with how work either takes energy out of a system or puts energy into it. Okay, so all these questions though are based around the same concept, that work is either taking energy out of the system or work is putting energy into the system. So I'm going to look at question number 20. I think 20, well no, let's look at number 19. We have a cart on the top of a hill that comes down and then runs into my car. Okay? It's going to create a dent in the car, but in order to figure out what that dent is, we're going to first need to know how much energy is in the system. Okay, so the idea is up here, the cart has 0 kinetic energy, okay, but the potential energy, we need to figure that out. Well, the potential energy will equal mgh. We're told that the hill has a height of 6.32 meters. So to figure out the potential energy in the cart at the top, we take its mass, which we're told is 0.75, times gravity, which is 9.8, times the height, which is 6.32, and we should get, roughly speaking, 46.5 joules. There are 46.5 joules in this system complete. There is no other energy in the system, okay? Because that potential energy is going to convert to kinetic energy as it comes down the hill. So when this cart gets down to this spot on the hill, the kinetic energy is now 46.5 joules because the potential energy is now 0. We've gotten all the way to the bottom of the hill, it can't gain more speed. And so that means that the potential energy is 0. So gravity has done work to convert that potential energy into kinetic energy. Now, as this cart runs into the car is going to do work on the cart cart's going to do work on, they're going to interact with each other, and we're going to notice that all of the energy in the cart goes away because it stops. And so the question we have is, if the cart slams into the car and stops, how big of a dent would it have created? Well, the idea is that the cart's doing some work on the car, and work is force times distance. Well, we know that there's this amount of energy in the system, so the cart can only do 46.5 joules of work. This is the one that gets a little tricky. People don't quite grab that idea that the cart is doing the work of its energy on the car. That does make it a little bit frustrating to understand. We're told in the question that the cart exerts an average force of 721 newtons. And we want to know, how far does it go forward? In other words, how far does the dent become before the cart stops? And so if we were to divide this by 721 on both sides, the depth of the dent will be 0.064 meters, which is roughly 6.4 centimeters. So this is an example of a problem that the problem had energy. The work that was done took the energy out of the problem. That's what stopped the cart from going through the car. There was work being done, force over a distance, but there was a distance traveled, but it was tiny distance traveled. Okay, the next little bit of stuff is all about understanding that energy is conserved, and that if there are no external forces, things would stay pretty consistent. So what we're going to do is we're going to look at the first question, question number 1. We have something like this. We got a car right here, or a box. It has an initial velocity. It's going to come down. We want to know what is the velocity here. And then the second part is how high up here on the side will it end up before it stops and runs out of steam, or runs out of speed. Well, the rule is that energy is conserved. So we're going to go from point 1 to point 2. In point 1, the box is already moving, so there is some kinetic energy, but it also has some potential energy. Now, without friction, there's no work being done. No one's pushing the box. It's already moving. That should equal the kinetic energy after the fact plus any potential energy after the fact. But if we call this 0 for h, then the potential energy there would cancel. So we really only have what's left here. Now there's something really cool about this. They don't give us the mass for the box, but if you start looking at the formulas, 1/2 mv1 squared plus mgh1 equals 1/2 mv2 squared. All of them have the same mass, so that mass can cancel. But if there's some friction or there's some push or pull, some external work, you cannot cancel the masses. That only happens if there's no external work. Okay, so this is 1/2. The initial velocity was 9.87, so we'll say 9.87 squared plus g, of course, is 9.8 times the height of the hill was labeled as 1.81 meters. That needs to equal 1/2 of v2 squared. So we have this number over here on the left. You guys can calculate that, but that needs to be times by 2. That'll get rid of the half. And then afterwards we take a square root of that to get v2. So the velocity at the bottom of the hill will equal 11.5 meters per second. So there's part A of that question. Now part B, okay, if this box, if its initial velocity was 0, and it was just given a little nudge off the edge, then it would have returned to the same height because potential energy returns to potential energy. However, because it had an initial velocity that was not equal to 0, it's actually going to make it up higher. But the question is, how high? So in this problem, we're going to go back to KE1, okay, plus potential energy 1 equals KE2 plus potential energy 2. Now the difference is, up here at its highest point, the velocity will equal 0, which means there will be no kinetic energy after the fact. Well, the good news is, all this work I already did down here, this thing, I'm going to circle right here in green, all of this, none of it changed. The difference is that it is set equal to m, which we would have already canceled, times gh. So we have our 9.8 h. So instead of taking that times 2 and taking the square root, we just divide by 9.8. I'm going to grab my calculator and walk you through the calculation. If I get it turned on. Okay, so right over here you can't really see it, but it's 1/2, so 0.5 parentheses 9.87 squared plus 9.8 times 1.81. Oops. Alright, someone was probably yelling at me right there. Okay, and then I need to divide that by 9.8 to get 2.31. So H2 is 2.31 meters. Is that higher than it initially started at? Yeah, it was originally only at 1.81. Now we're at 2.31 meters. Okay, so that's how we would deal with question number 1. The idea is kinetic energy, potential energy, they're interchangeable. We can trade one out for the other. Hopefully that helps. And last but not least, I want to grab a question from the back page. And we're just going to talk about, and these are all essentially set up the same way. But let's look at question number, let's do question number 7. 7 is one of the only ones where the angle actually matters. So it says unknown force is applied to a 12 kilogram mass. So here's my 12 kilograms. And the force is applied 30 degrees above the horizontal. So there's a 30-degree angle there. That's my force. And it says determine the force acting if the force acts as a horizontal displacement of 22 meters, okay, and increases the speed. Sorry, I got interrupted. I got to think where I am. So we're going to go 22 meters of displacement. The velocity and increases the speed or the velocity from, we're going to say V0 or V1, sorry, is 11 meters per second, and V2 down here is 26 meters per second. And so we're going to go through and we're going to try to approach this in much the same way we would any of these problems on the back page here. First thing we're going to notice is we're going to ask, is there kinetic energy at the beginning of the problem? The answer is yes. If I look at potential energy at the beginning of the problem, well, this doesn't say anything about being on a hill. It never talks about height changes. So if there was potential energy, it never changes, which means it would be equal to the potential energy 2. So those can cancel each other. I mean, if we're up on top of Mount Everest doing this, but we're not going down the hill at all, yeah, there's potential energy, but if it never changes, it doesn't affect the question. Is there kinetic energy after the interaction? The answer is yes. In fact, there's more. Well, in order for the energy to go up, that means there must be some work from an external force. Okay, and so I have the original kinetic energy plus the push or pull that equals the final kinetic energy. Yeah, that makes sense. I added some energy in. Okay? So what this leaves me with is trying to fill in all the information. 1/2 mv1 squared plus, now work by an external force, because I'm trying to figure out how much force there is. Well, work, remember, is FD cosine of theta. Now, a lot of the problems, the angle theta turns out to be 0. In this problem, it's not. It's actually 30, so that matters. This should equal 1/2 mv2 squared. This is an example of a problem when the mass doesn't cancel, because right here in the middle, the FD cosine theta doesn't have m as part of its equation, so we can't cancel the mass. What we can do, though, is start by plugging in all the values that I do know. For instance, this is 1/2 a mass of 12 times a velocity of 11 squared, plus F, I don't know. D, the displacement, was 22, and it's the cosine of 30 degrees. Your calculator has to be in degree form, or degree mode, and that will equal 1/2 the mass of 12 times a velocity of 26 squared. If we throw this in, this turns out to be a 726, so I'm going to minus 726 from both sides. And keep going. Let's grab my calculator, I guess. If I'm going to calculate some of these, you should do it in front of you. Over there I have 0.5 times 12 times 26 squared. It's 4,056. I'm minusing 726. Oops. And that gives me 3330. So now I have 3330 equals, and I'm going to take a second and find out what is 22 cosine of 30. And I'm going to check my mode real quick. I've got it in degree mode. Press enter, gives me 19.05. So 19.05 F. So I'm going to divide by that 19.05. I'm going to take 3330 divided by previous answer, and I will get 175. So the force here would be 175 newtons. All right. That's not everything that you're doing on there, and I understand there's going to be some challenges, some things you come back and have confusion on, but I hope that that's enough to kind of get the juices flowing, get the ideas of how to solve these problems going. Good luck. We'll see you later on, and be good for the sub.